I think it should be. Yeah, I think it should be last.
I think it's. Let me. I'm just sorting by updated. Okay. Well, here we can preview it really quick. Oop. Which
It's the latest one.
does that seem right?
Wait, doesn't why is it shaped like this?
It's just a visual. Okay.
So welcome back, everyone, for session 4B about the high redshift universe and galaxy surveys in the high redshift universe. So we'll start with a talk from Jinyi from University of Arizona, who's going to tell us about probing the early universe using distant quasars. So yeah, now that the technical issues are resolved, we'll have Jinyi Yang telling us about the early universe and probing the early universe with distant quasars. And so you have 25 minutes.
Thank you. Can everyone hear me? Yeah, thanks. Thank you so much for this opportunity. So today I can introduce my recent work about using the most distant quasars to probe the early universe. And I'm Jin Yang from Steward Observatory. So I was briefly talking about the reionization in quasars and show some preliminary results from the JWST, GTU, and CQ1G observations of these high redshift quasars. And I will talk about what we can, how we can use Roman to study these high redshift quasars. So first, the brief introduction about quasars. As we know, so quasars are kind of compact and it's active galactic nuclear. It's kind of galaxy, and we can see the structure here in the center of each quasar. There is a supermassive black hole. We can also see the outside region. We can see the accretion disk and the broadline region, narrowline region. And so quasars have they have high luminosity powered by this central supermassive black hole. So it's always extreme high luminosity. We can go to distant the universe using these quasars. And from observations, we can quasars, we get spectroscopy observation tell us about the parallel continuum first, and also broad emission line on the parallel continuum. That's the quasar spectral, a typical quasar spectral. And also we can see absorption features on this continuum emissions. That's what we can learn from the spectroscopy. And also the observation tell us quasar, they have multi-wavelength emission from X-ray to radio. Some of them have been observed with variability features. So, based on these basic properties of quasars, if we go to higher redshift, to the reionization epoch, what we can learn using these quasars. So here I mean the reionization era quasar, I mean the redshift above 6, which is about 900 million years after the Big Bang. So we can learn these quasars, these high redshift quasars provide us with unique and valuable information on of this supermassive black hole at the early universe, early massive galaxies, and also the intergalactic medium evolution during the reionization epoch, and also the intervening metal observer and tell us about the metallicity evolution at the early universe, and also the overdense environments, early massive halos, and large-scale structure surrounding the quasars. So all these science topics tell us why we want to learn, why we want to study of these high redshift quasars. I will show some example that how we can use these high redshift quasars to study the early universe. And the first one is IGM evolution during the reionization epoch. As I showed before, there's a typical quasar spectrum, and blue are the Lamarck line, there was continuum emission. However, if we go to high redshift, there's the Lamarck emission line, bluer part that the significant feature showing the quasar spectra that's absorbed by the neutral hydrogen in the intergalactic medium at high redshift. So we can see quasar Prism zone, quasar Lamarck Gunn-Peterson trough, and this is a complete observed trough. And also Lamarck lemon beta forest, that's the residues from the neutral hydrogen in the IGM, the absorption by the neutral hydrogen in the IGM. So we also call these residues transmission spikes. All these features, absorption features showing quasar spectra can be used as direct tracers of the IGM evolution, can be used to estimate the neutral hydrogen fraction as a function of the redshift. So here is a figure show the quasar, or the estimate of the neutral hydrogen fraction from using quasars, using high redshift quasars, from redshift 5 to redshift about 7.5. Use different methods. For example, that's the Lamarck lemon beta effective optical depths, dark pixels, and also quasar damping wing absorptions. At redshift above 6, we can see there is a, due to the significant increasing of the neutral hydrogen in the intergalactic medium, so it's very hard to directly provide direct constraint on the IGM, on the neutral hydrogen fraction in the IGM. So we only get the upper limit based on the dark pixels. This work is led by a graduate student in our group, Jinyi. So we just got this result here. That is so far the only one constraint from quasars at this redshift. To higher redshift, we just get the quasar damping wing estimate. However, we can see the large error bar. That is limited by the current spectroscopy observation from ground-based telescopes, and also the, for example, the modeling of the quasar intrinsic spectra. So that's measured. And so this part actually raises questions that we need to use with telescopes to better constrain the IGM evolution. And then, as I mentioned, the quasars, they're central supermassive black hole in these quasars. So we can learn about the supermassive black hole growth and black hole host galaxy co-evolution. As an example here, show the left one show the high redshift quasars, red squares at the redshift about 6.5 quasars, compared with this black dot at the redshift 6 quasars, and comparing with the SDSS low redshift populations, that's the black contours. As we can see, we have already know that this high redshift luminous quasars, they're the supermassive black hole, they're accreting with high accretion rates close to the Einstein limit. And they have the black hole mass about a billion solar mass black hole. So this result actually is challenging the early supermassive black hole growth model and also the black hole seed model. As we can see, the black hole growth tracks from redshift 30 to the redshift we observed that that's the billion solar mass black hole. Here that we require a very massive black hole. So our result is actually consistent with a more massive seed black hole model. However, we still cannot get the exactly conclusion. We need a larger sample and we need to measure the black hole mass more accurately. And also the black hole host co-evolution. This is actually showing this figure. It's just the possible evolution passes between the co-evolution of the black hole and the galaxies from the early universe to what we can observe today. We can see these three different possible evolution paths. Observations so far, the observations of high redshift quasars, in particular the luminous quasars, tell us that there could be overmassive, supermassive black holes compared to the host galaxies, and relative to the relation we learned from local universe. That is the solid line, also dashed line. And here is the red and orange pointer from high redshift luminous quasars. However, here the observation is limited by the wavelength coverage or our understanding about the quasar host galaxies from sub-millimeter observation of the C+ line. That is the far infrared emission from the quasar host galaxy. We can now detect we cannot directly detect the stellar emission from the quasar host galaxy directly, even with HST. That is the HST image. We can see after the PFS subtraction, the residual, the red panel here shows us there is no detection outside of the central noisy core. So which means that we, all of this limited our understanding of the co-evolution between the supermassive black hole and the host galaxy. So that is also what we want to learn from space telescopes. And then the overdensity environment. So theoretical model predict that these luminous quasars, they should reside in overdense regions, as shown in this figure. That's the simulation. So surrounding us, the central supermassive black holes, we should see the overdense environment. However, observations show inconclusive results, as we can see in these two figures. Surrounding the quasar in this field, we can see overdense region around this quasar. However, in this field, we do not detect any overdensity in this field. So this is also, we want spectroscopy observations. We want complete spectroscopy observations surrounding all this high redshift quasar field to find an answer and whether these quasars reside in the overdense regions. Over this science point I mentioned, there are the reasons why we want to learn high redshift quasars. However, this reionization era quasars, they're very rare. And we can see here is the quasar number density from low redshift to high redshift. There is a rapid decline since redshift about 5.5. We can see here is significant rapid decline towards high redshift. At the same time, we also have a very significant contaminant. They could be hundreds to thousands higher than the quasar number density within the depths of our current surveys, that is 21 magnitude in J band. We can see the contaminant as MRT dwarf or early type the red galaxies. So I want to mention that so far we have a relatively larger quasar sample at the high redshift, at redshift above 6. That is based on all the effort from the high redshift quasar astronomers in the past 2 decades. And here is the, just mainly we are using this optical and near infrared public survey data that sees the scale coverage of these surveys. And here is the recently our luminous quasar survey. Ooh. Oh yeah. Just 8 years ago, that we see more and more quasars. We got a redshift about 6.5, and or is red point from our luminous quasar survey. So now we have already constructed a relatively large high redshift quasar sample. After the launch of JWST, so we can JWST opens a new era. Then we can observe large sample of high redshift quasars using JWST. Here is the magnitude redshift distribution of our known quasars and also JWST targeted quasars. And JWST is targeting a large sample of redshift about 6 quasars, covering a wide range of the redshift and also luminosity. So then next I will show some preliminary results regarding this study of these high redshift quasars from different aspects. The first part that is the quasar rest frame optical emission and the supermassive black hole mass. Here is a template of the quasar spectra. From ground-based telescope, we can cover the quasar spectra until this region, that is rest frame UV, rest frame 3000 angstrom. So if we want to measure the quasar black hole mass, we can only use carbon 4 and maximum 2 line for the virial black hole mass. However, we know that both of them, they are not the most reliable tracer. If with JWST, we can now cover the H-beta line, oxygen-3 H-alpha line, and in particular, the H-beta emission line. This one is thought to be the most reliable tracer of the real single epoch virial black hole mass. So that is what we want to use to estimate the black hole mass. And some preliminary results. From the JWST cycle 1 observations, we already get some spectra of these Redshift quasars. For example, this is some quasar early result from the Aspire program. I will introduce this program later with details. We can see some H-beta line, oxygen-3 line here. We can see diverse emission lines, in particular for the oxygen-3 line. Some of them with broad and blue shifted oxygen-3 component. Some of them we do not detect the strong oxygen-3 emission. And also some of them we see strong narrow component. And based on this observation of the rest frame optical spectrum, we can first measure the H-beta black hole mass, as I mentioned before. Now we can also compare the H-beta black hole mass with the maximum 2 black hole mass that we have already obtained. So here is showing the results. The conclusion is they're generally consistent. So which means these H-beta observations can confirm the existence of the billion solar mass black hole at redshift above 6.5. And I also want to mention there's a small trend of the slightly smaller black hole mass from H-beta, but we are waiting for a large sample for statistics. And I also want to highlight this one we just got a few weeks ago. That's amazing result for the Redshift 7.5 quasar. This is actually the first one covering the rest frame UV and optical for Redshift 7.1 quasar from the lemma alpha to the H alpha. This is a combination of the near spec fixed Lee data and also the mirror MRS data. We can also compare the spectra with the ground-based blue point, the ground-based photometry data, and also JWST near-cam photometry data. And this one is from a program we call it the Quasar Frontier program. Yeah, and also here we're targeting these three, the most distant known quasar, the redshift around 7.5 with multiple imaging and spectroscopy of the remote. And then after we're talking about the black hole, which moved to the host galaxy, as we mentioned before, previously even with HST, we can now detect the stellar emission from quasar host galaxy directly. But now if we get JWST near cam, so we can see here the first sample of the luminous quasar sample from the Aspire program, and here's the near cam imaging 2 filters. This is the original imaging, that's the quasar image. You can see the point source here. After the PS subtraction, we can get these 3 different tabs. Some of them we get this clean, almost no detection surrounding the quasars, and which means that's a weak or compact host galaxy emission. And some of them we significantly detect the host galaxy. You can see it's extended emission and it looks dusty. And for some system, we confirm that they can be quasar companion system, even also with multiple companion system here. So this is what we can learn from the luminous quasar, and also from there is a faint quasar sample in JWST cycle 1 targeting this HSC faint quasar sample at redshift about 6. Here's an example in 2 filters. We can see also in the right band, we can see significant host galaxy emission. And with this detection of the quasar host galaxy, we can revisit the black hole mass and the host galaxy stellar mass figure. As I mentioned before, some observations from ALMA suggest that overmassive supermassive black hole. However, when we're looking at the JWST near cam of these faint quasars, we get this, there seems no evolution from low redshift. These 2 points are from the 2 HSC faint quasars, and orange contours are the predictions based on the redshift 0 relation, which means assuming no redshift evolution. And the locus should be here, and we can see the 1 sigma, 2 sigma, 3 sigma. These 2 are consistent with the no evolution assumptions. So this result now tell us that it could be that this high redshift quasars are consistent with low redshift black hole host relation. Again, we also need a larger sample for statistics. And then we can also looking at the black hole host interaction directly using the imaging or spectroscopy observations. For example, here is the spectral, the near cam slitless spectral. That is a 1D spectral. This one I showed before. I mentioned that is broad and blue shifted oxygen-3 emission. This is one of the most extreme case we discovered. And we can also see the extended emission from the 2D slitless data. That's from the spectroscopy only. And with the near spec IFU data, we can get both morphology and also gas kinematics. Here is a few examples recently published this year. So we can see the redshift 6.8 quasar, luminous quasars, we detect a significant residue of the oxygen-3 emission. And here is the redshift 7.5 quasars. That will be, we will hear more details from Weizhe Liu's talk this afternoon. And also, I want to highlight this one. This is the multi-giant quasar companion system at redshift above 6. And we can see the blue part that show the C+ emission observed from ALMA, and the colorful the orange and red one, that is the oxygen-3 emission from near spec IFU. Over this aperture here, we obtained a very high quality spectral from all this within this aperture, so we can get the kinematics about this gas, and we can learn more details. We can get more details about the story of this system. That will tell us about the story of the assembling of the early quasars with the supermassive black hole and the massive host galaxies. So that is the black hole host. Then if we talk about environment, JWST also reveals some evidence about the overdense region surrounding these early quasars. This is the JWST GTO program Eiger, and target 6 luminous quasar redshift around 6. Here is one example. This is the quasar spectral. Along the quasar sightline, we have already detected multiple galaxies from redshift 5.3 to 7, and we can see here, this is about quasar redshift, and we can see there is overdance of the galaxies associated with the central quasars. So there could be overdensity environment of the quasar. And also to have redshift of 6.5, this I mentioned before, the Aspire. This is actually a NIRCam's last survey program for about 25 quasars, a redshift above 6.5. And this is a medium-sized JWST Cycle 1 program together with a 100-hour, this is ALMA-led program, so searching for the quasar environment in the multi-wavelengths. And from the JWST observations, that is the oxygen-3 emitter figure. This program has already spectroscopically confirmed more than 500 galaxies at redshift 0.3 to 7. And we also found that some of them, they are associated with quasars. This is one example in one field. So we have already, this is the center is a quasar, and we see the surrounding galaxies. This is an overdense region, and also these galaxies, it seems that they are aligned to a large-scale filament structure. And more details about our program can be found on the web page here. So as a brief summary, so overall I mentioned about there's a preliminary result from JWST. And so far, JWST provides us the study with the existing quasars, very deep and unparalleled studies of these existing quasars at redshift above 6. And this result, actually, they're changing our understanding from multiple aspects, for example, central supermassive black hole host galaxy, environment, and AGM evolution. However, I need to mention, JWST is now designed for a wide field survey of these new quasars. That is why we want to the next generation survey facilities, for example, Roman. So with Roman, how we can probe these most distant quasars and study the early universe. The first one, the Roman steps, as I show you figure here, will along the surveys of quasars up to redshift 9 to 10, with about hundreds or more than hundreds quasars that depend on luminous function. And so with about hundreds quasars above redshift 7, as shown figure here, that is the depth about the high latitude wide area survey here. So redshift 7, 8, 9, now we can see different numbers expected, predict based on the current quasar luminous function. So this is what we expect about the new quasar surveys. And here, for these 4 filters, our group, we are already working on the color selections for these high redshift quasars at different redshift range. So we will hear about more details from Weilong's talk this afternoon. And that's about the quasar selection. So I also want to highlight some specific points. With Roman steps, we can also have wide field surveys of faint quasar and AGN, so we can look into the faint populations. Here is a point, is a question raised recently by JWST observation, that's the red dot and AGN fraction question. So there's some red dot from the covered reviewed by the JWST near-cam image. For example, here we can see it's unresolved, and also the near-cam SED can be well fitted with a type 1 AGN. Additionally, some spectroscopic observations of high redshift galaxy reveal the broad component of the HR emission line. Then these observations raise a question about a higher AGN fraction at high redshift. So regarding this part, we will have an answer from Roman with a complete wide field spectroscopic survey of the faint quasar or AGN. And also, so we will highlight the Roman's high spatial resolution and high sensitivity will allow us to carry out a systematic survey of the gravitationally lensed quasars, or in particular at high redshift. Oh, sorry. We know that there's only one lensed quasar known at high redshift above 6. And this one is actually discovered based on the ground-based photometric imaging data. As a comparison here, here's HST image. We can resolve this system. It's a very compact lensed quasar system. However, with the ground-based image, this is the pan-star image, we cannot resolve it. So Roman's spatial resolution will be comparable to the HST, which means we can directly resolve it from the imaging data. Then we can carry out a systematic survey of them. And then this reionization, as I mentioned over this quasar surveys, we will get a larger sample of this faint quasar or a large sample of high redshift quasars. Then we can study the IGM evolution during the reionization epoch directly. Here is the simulation. That is the individual constraint is constrained based on the individual quasars at redshift above 7. We can see the larger error bar and also just only a few points here. And here's the simulated for all existing quasars. We can get better constrained, but still just up to redshift about around 7 or 7.5 with a larger error bar. If to next generation, we get a larger sample of the quasars, we can directly get the trace of the IGM evolution as a function of redshift from 6 to 8.5, and with much better, much improved the error bar here. So this is where we can learn about the reionization from the, for example, Roman quasar sample. And also quasar environment, as I mentioned from JWST, we already get some evidence about the overdense regions surrounding high redshift luminous quasars. However, I want to mention that JWST near-cam, the field view is relatively small, relative to overdense region surrounding quasar. Here's an example of redshift 6-ish quasar overdense region. We can see the size is about 15 arc-minute here. So which means it's much larger than the JWST near-cam field view. And with Roman's large field view, we can cover such kind of large scale overdense region with only one pointing. That is the Roman can tell us directly mapped overdense region. And that's a summary. So with JWST, as I mentioned, we get more details. We can go deeper for individuals. And Roman is good for surveys for redshift above 6 quasars with deeper wide field up to higher redshift and larger and diverse samples. And also, as we already learned that Roman has high sensitivity, high spatial resolution, and also large field view. So we can also, it can also allow in-depth study of this interesting individuals of high redshift quasars. Yeah, I'll stop here and take questions. Thank you.
So thank you very much. Questions in the audience here or online as well? So there's one question over there.
Thank you for a very exciting talk. So I was wondering, you mentioned that you have ALMA data as the 158 micron line. Do you also have CO for what fraction of the sample? And if you have this CO, or if this CO is coming, can you predict where those sources will go on the M sigma relation? Because you showed that some of them are off the local M sigma. So where will they go?
Thank you for the question. CO line, actually for the high redshift quasar, CO observations is relatively hard. We only have very few, very limited sample at high redshift with CO emission, with CO observations. Yeah. So, but I think we are building the sample. I mean, just Typically, just after we get the C+ emission lines, if the C+ is relatively bright, we can do follow-up with the CO line, and we can learn more about the host gas kinematics from the CO lines. Yeah. Thank you.
Do we have any questions online? More questions from the audience? In the meantime, I'll let you think. I'll have a little question. So there has been evidence, at least from lower redshift up to redshift 2 or 3, that radial load AGNs are better probes of over dense environments compared to radio quiet and AGNs or quasars or radio galaxies. So I was wondering if you have any estimates on the radio power of your sources and if there is a correlation between that and the nearby environment.
Yeah, very good point. Yeah, thank you. Yes, and see for this high redshift radio quasars, there are also some prediction and also observations, but we just get few data now. We are working on a large program of high redshift radio quasars to study the surrounding overdense regions. But so far, for this result, there's no radio. There's one just observed. Yeah, a few weeks ago. Yeah, we haven't got the data, or we haven't got the result now. But for statistics, we need a larger sample for the radio source. Yeah. Thank you.
Thanks for a great talk. So I was wondering about your black hole mass from magnesium 2 and H beta correlation. So I think that, I mean, they are kind of consistent within maybe the errors, within the contours, but a lot of them seem to be kind of above the relation that you mentioned. They seem to have smaller H beta masses. I was just wondering, are these sources, do they have a certain Eddington ratio? Or are they selected to be above or at or certain ways? And how large of a sample are you expecting that you might be able to populate and understand this relation a little better?
Yeah, thank you for the question. Here I show there are only the quasars from the luminous sample. In our luminous sample, they have a narrow Eddington ratio. And we can see there's 8 points there. And we can see they're consistent, but we cannot get exact conclusions. So after we finish over the JWST cycle 1, over the data combined, we actually have 30 or 40-ish quasars. Then we can get better statistical. And also I mentioned there's a slight, there's small trend. Oh, we actually don't know whether it's correct or not, so far. So, but with 30 or 40-ish, we will know that. And we also can get a scattered, compared to the low redshift. Yeah. Thank you.
I have time for one more quick question. If not, there is nothing online. No? If not, yeah, let's thank the speaker again. Yeah. It's one of your talk.
Yeah. Perfect.
So next speaker, we have Yuichi Harikane from University of Tokyo, and he's going to tell us about high redshift galaxies from JWST and implication for Roman. So you have 10 minutes.
Okay, so hello everyone, I am Yuichi Harikane from University of Tokyo. So I thank organizers for organizing this very nice conference. So today I will talk about the JWST result about very high redshift galaxies and its implication for Roman surveys. Okay, so this figure shows the history of the universe. As you know, the first galaxy and the first star may form at redshift 12, 20 to 30. Then these galaxies evolve to the cosmic ray, then final cosmic time, then finally it turns out to be the galaxies that we observe in today's universe. Then in this context of the galaxies, galaxy formation and cosmic evolution, Observing the high redshift galaxies is important to understand several important processes such as early galaxy formation, evolution, star formation, and high redshift, including star formation efficiency and initial mass function, and galaxy age and relation. And one of the most important quantity in the galaxy observation is the star formation rate density. So this figure shows the star formation rate density as a function of the redshift. So axis shows the cosmic average of the star formation rate per cubic Earth volume. So this black point shows the observations from the Hubble, mainly from the Hubble HST observations. So these HST observations show that the star formation rate density increases monotonically from the early universe to redshift 2, then decreases from redshift 2 to 0. And several studies report that this kind of evolution can be explained by the model assuming the constant star formation efficiency across the redshift. So this red curve is a model assuming the constant star formation efficiency, and if we assume this model, and then we can nicely reproduce the redshift evolution trend from redshift 0 to 10. And also this model starts to predict the steep decline of the star formation rate density at redshift beyond 10. And JWST is following this redshift range. So we high redshift astronomers want to select high redshift galaxies with JWST and want to understand star formation in this very early universe. So now JWST is finding many high redshift galaxies. So in our earlier work, we use ERO and ERS narrow imaging dataset, and we select a total of 23 galaxies candidates at redshift 9 to 16. So this figure shows the UV magnitude as a function of the redshift, and this red diamond shows the JWST selected galaxies. These black points show the HST selected galaxies. So with this figure, you can easily understand the power of the JWST to probing the high redshift universe. Then using this data set, we calculate the UV luminosity function, which is a number showing the number density as a function of the UV magnitude. So this figure shows the UV luminosity function at redshift 9 and 12. So this red diamond shows the JWST, our result from the JWST observations. So JWST observations are consistent with other HST and other JWST observations at redshift 12 and redshift 9 and 12. Then we compare the JWST observations with model predictions. Okay, so left panel shows the UV luminosity function again. This red diamond shows observations, and this blue curve shows the model predictions with different theoretical model predictions. Okay. As you can see, some of the models underpredict the number density of this kind of very bright galaxy, of this very high redshift galaxy, and especially for the bright regime. Maybe right panel may be more easy to understand. So in this right panel, we just show the number of the galaxies at redshift beyond 12 and magnitude brighter than minus 20 magnitude. So in our earlier data set, there are a total of 4 such very bright and very high redshift galaxies. And this blue histogram shows the number from the theoretical predictions. So all of the theoretical models underpredict such number of the number of such bright and high redshift galaxies. So JWST is now finding many galaxies whose number density is surprisingly higher than model predictions. Yes, then we calculate the cosmic star formation rate density. So we calculate star formation rate density and star formation rate from UV luminosity using this equation. So here KUB is a conversion factor from the UV luminosity to the star formation rate, and here we use this value for the salpeter initial mass function. So this figure shows the star formation rate density as a function of the redshift, and this red circle shows the JWST observations. So please compare this JWST observation with this blue dashed line. Okay? So this blue dashed line is a model assuming the constant star formation efficiency across the redshift, which I showed in the introduction. As you can see, this model can nicely reproduce the redshift evolution trend from redshift 0 to 10. However, this model starts to underpredict the star formation rate density at redshift beyond 10. So there is a tension between the JWST observations and the model predictions. So this tension may indicate something, some physics may be different at high redshift. However, there is one caveat. All of these has the data points based on the photometric candidates of the high redshift galaxies selected with the narrow imaging dataset. So there is always a concern about the low redshift interlopas. So for example, the previously claimed Redshift 16 galaxy candidate, actually from the mass spec spectroscopy, it turns out to be a Redshift 4.9 low Redshift interalphas with very strong H alpha and O3 emission lines, which mimic, which has boosted the broadband photometry and which mimic the Lyman break-like shape in the NACAM imaging. So we definitely need a mass spec dataset to discuss whether the star formation rate density at high redshift is high or not. So that's why we are now investigating the non-spec dataset. So far, there are a total of 25 galaxies spectroscopically confirmed at redshift beyond 8.5. So this figure shows the UV magnitude as a function of the redshift, and this red diamond shows the spectroscopically confirmed galaxies. This includes the very famous bright galaxy GNZ11, which I will discuss later, and also the new redshift confirmation at redshift 11.04, which shows a very clear Lyman break and several emission lines. So based on this dataset, spectroscopic dataset, we obtain the lower limit of the star formation rate density, which is indicated with this red diamond. Still, this lower limit shows higher star formation rate density than these model predictions. So from the spectroscopy, we still have to find the kind of tension between the JWST observations and model predictions. Okay. Then there are several physical interpretations for this high star formation rate density or high UV luminosity density at high redshift beyond 10. For example, one natural explanation is that high star formation efficiency because we are comparing with the constant star formation efficiency model. So if the star formation efficiency is higher than 5% at redshift beyond 10 compared to the lower redshift universe, then we can naturally explain this high star formation rate density. The other possibility is that many AGN populations, so recent JWST mass-spec observations are finding many AGN whose number density is higher than our predictions at high redshift. And this is also possible. So this kind of many AGN population may boost the UV luminosities at high redshift universe. The third possibility is the top-heavy initial mass function, IMF. So in a theoretical perspective view, if we go to high redshift, then because the metallicity is low and CMB temperature is high, the IMF becomes more top-heavy. So for example, this figure shows the simulation for the IMF at redshift 10 with moderate metallicity or 10% metallicity. So even 10% metallicity, because the CMB temperature is high, the IMF becomes more top-heavy than salpeter initial mass function. Okay? So right panel shows that KUV, which is a conversion factor from the UV luminosity to the star formation rate. So this black line is our assumption. And if we assume normal initial mass function, then this KUV conversion factor is similar to this our assumed value. However, if we assume top-heavy initial mass function, then this KUV conversion factor significantly decreases because this top-heavy IMF makes many massive stars which boost the UV luminosities in the galaxies. So this kind of top-heavy IMF can also explain the high UV luminosity density at redshift beyond 10. So from JWST observations, we are now finding many galaxies than our theoretical model predictions and finding excess in the star formation and densities, which can be explained by these three possibilities. So far, JWST are finding many galaxies. However, regarding the bright galaxies, there are only a few, and there are only a very small number of the galaxies. This is because HST and JWST as imaging observations have a very small area due to the small wide field of view of the HST and JWST imaging instrument. However, these bright galaxies are very interesting. For example, this one, GNZ11, this is a spectroscopically confirmed galaxy at redshift 10.6. This is very bright, about minus 21.5 magnitude. And as shown in this spectrum, it shows multiple emission lines. And interestingly, these nitrogen emission lines are very strong. This indicates a supersolar nitrogen over oxygen abundance ratio at redshift 10 or 11, which cannot be easily explained by models. And also some studies report the AGN in this galaxy. So this kind of galaxy, very bright galaxy, is very interesting. And actually, we think that Roman can find 100 or 1,000 this kind of very bright GNZ11-like galaxies. So by including long wavelength observations, imaging observations in Roman surveys, we can nicely investigate the very rare and bright galaxies compared to JWST observations. Okay, so this is the last slide before my summary. So if we go to relatively lower redshift, then the Subaru and Roman has a synergy, has a very excellent synergy in observing and investigating galaxy evolution. This is because the Subaru HSC and PFS imaging and spectroscopic instrument have a wide field of view, which is in excellent synergy with the wide field of view instrument of the Roman. And if we want to realize this kind of Subaru-Roman synergetic observation, choosing survey fields that can be observed with Subaru is very important. Okay, so this is a summary of my talk. So JWST is now finding many galaxies and theoretical model predictions which can be explained by high star formation efficiency, AGN, or top-heavy Reynolds function. And Roman can find more than 100 or 1,000 bright galaxies at redshift beyond 10. That's it. Thank you.
Thank you very much. Now, questions for Yuichi. We have 5 minutes. You can ask a question.
Oh, okay. Sorry, really interesting talk. Thanks so much. I had a quick question about the top-heavy IMF result. I'm sorry if I missed it, but what type of top-heavy IMF are you assuming? I mean, I'm shallow or top-heavy high mass slope shallower than saltpeter. Is there a what's the exponent that you have to assume to make your model work?
Yeah, I didn't explain detail. Yeah, thank you for this question. So here you can see two Hassen models. So one top 3-1 is a kind of saltpeter slope, but is different cut, mass cut from 50 solar mass to 500 solar mass. And for this purple dashed line, this is a kind of shifting. This is assume a different shape of the different slope of the IMF. Yeah. So we assume the two different top heavy IMF which are reproduced, which makes low KUV conversion factor.
More questions? Online? And so I was wondering for the redshift above 12. So, I mean, those are rare galaxies, very bright. So I was wondering if you have evidence for any of them to be actually associated with maybe over densities. So that would boost up the density that you measure.
Yeah, that's a very good point. Yeah, it's possible that if you observe bright galaxies, yeah, they can be in the overdense region. And actually this error bar, this already includes this kind of cosmic variance effect. So including the cosmic variance effect, still, it shows high star formation and densities and model predictions.
More questions? So let's thank you again.
Yes, master.
So next speaker, we have Minghao Yue, who's going to tell us about lens quasars in the epoch of reionization.
Hello, can you hear me? So yeah, I'm Minghao Yue, and I'm a postdoc at MIT Cavity Institute. So first of all, let me say a big thank you to the conference organizers and all my amazing collaborators. So today, I'm very happy to get this chance to talk about high redshift gravitationally lens quasars and how Roman can be a game changer in this field. All right, lens quasars. We all know that gravitationally lens quasars are very valuable, useful objects in astronomy because it enables many important studies. For example, people have been using lens quasars to measure some key cosmological parameters, especially the Hubble constant. And we can also use lens quasars to probe, the structures of the foreground lensing galaxy, especially their mass profiles and their CGM structures. And also, with the help of lensing magnification, we can get a magnified view of the supermassive black holes and their host galaxies, meaning that with lens quasars, we can probe the faint quasar population as well as the small-scale structures in quasar host galaxies. Well, I would say in principle, you can carry out these studies for lens quasars at all redshifts. But in this talk, I'm going to specifically focus on high redshift lens quasars, because I think there are some special points about high redshift lens quasars. Well, I mean, if you are primarily interested in cosmology, if we have some high redshift lens quasars that are suitable for this cosmological measurement, we can extend the redshift space towards, redshift 5, 6-ish, and that will give us a better constraint on these cosmological parameters. And also, if we are interested in, say, the redshift evolution of the galaxy structures, and then we do want to find some more high redshift lens quasars that are likely lensed by, higher redshift galaxies. And to me, I think the most important point here is, lensing magnification is naturally more useful for high redshift objects because, objects are at higher redshifts are fainter. So that means there are some studies that we cannot do with, non-lensed objects that we can only do with lensed objects. Well, just as an example, here I'm showing the lens quasar at 6.5 that Jinyi just mentioned. This is over 39. We discovered this lens quasars a few years ago, and ever since then we have been gathering, multi-wavelengths follow-up observations of this system. And as I mentioned, there are some faint signals that are usually not available for high redshift quasars that we do detect for this quasar. For example, the CO lines that we just mentioned, usually it's not available for a quasar at redshift beyond 6. But for this lens quasar, we can sample the nearly entire CO ladder for this quasar. With these, we can do some very detailed analysis of the host galaxy's gas content. Well, I'm not going to go to details of these studies, but my point is that with lensing magnification, we can do many important studies that are otherwise inaccessible. So I probably should mention that there is, this quasar is a target of JWST near-spec GTO observations, and I'm very looking forward to their results. Well, that is why we want to find more lens quasars at high redshifts. But unfortunately, this one is still the only one we have confirmed beyond redshift 5. So, so far, the sample of quasars beyond redshift 5 has, we have more than 700 known quasars, but over 39 is still the only one we have confirmed that is lensed. So these numbers infer a lens fraction of about 0.1%. Well, in comparison, there are some theoretical studies that are trying to predict the lens fraction of high redshift quasars. Well, their results range from 0.5 to 10%. That's a wide range, but that's because this fraction depends on the quasar luminosity function you assume and the foreground galaxy population and also survey depths, etc. But my point is, even in the most conservative case, these comparisons still suggest that we might be missing a large fraction of lens quasars at high redshifts. Well, if you wonder why this is the case, we can have a look at some simulated images of high redshift lens quasars. And by looking at these images, my feeling is that, first of all, many of them are kind of blended. These are simulated as LSST images. That tells me, usually ground-based spatial resolution is not going to be sufficient to resolve the lensing structure, making it very difficult for us to identify these objects. And also, the foreground galaxy in these systems are pretty bright compared to the background quasar. That means, traditional surveys for quasars heavily rely on their colors to, identify promising candidates. But with the contamination of the foreground galaxy's flux, usually the color selection will just fail for these objects. So that's another reason why we kind of fail to find most of the high redshift lens quasars. Well, keep these points in mind. I start to realize that Roman will be a very ideal facility to do, surveys for lens quasars, not only because it has a very sharp PSF, allowing us to fully resolve the lensing structures, but also, in addition to imaging and photometry, Roman will also provide spectroscopy, meaning that, well, if you imagine we get the spectrum of these objects, then we don't need to bother color selection, you know. We can see the features of the background quasar and the foreground galaxy, and we can confirm it's a lens quasar. So I should also mention that Roman has a pretty large survey area, allowing us to build a good sample of these objects. And I mean, motivated by these considerations, I asked myself, how many lens quasars at high redshifts are we going to be able to detect with Roman? And how should we find these objects? All right, in order to predict or to estimate the statistics of lens quasars, well, apparently we need to have some information about the foreground galaxy population and the background quasar population. And with this information, we can do some simple math to get the statistics of lens quasars. Well, here by statistics, I mean not only the number of lens quasars you can detect, but also something like the distribution of lensing separation and the distribution of foreground galaxies, redshift, etc. So, well, I decided to write a simple piece of code to do this job, and it turns out it works pretty well. So I can get all these statistics by running my code with, 1 minute or 2. And I have validated this code against some mock catalogs to make sure that it works. In here, I'm going to consider 2 populations of objects. The first one is luminous quasars, as we all know. And the second one is kind of a newly discovered population, that is the faint AGNs that are, newly discovered from recent JWST observations. Well, if you are not familiar with these objects, this is what they look like. And you can see in near-cam images, these objects appear to be point-like sources that have pretty red colors. And they have broad H-alpha emission lines that indicates there are active supermassive black holes accreting material in their center. Okay, now I can predict, the statistics of lens quasars and these AGNs in Roman. And I also consider, 2 upcoming surveys, Euclid and LSST. And now we can have a look at the results. So first, let's consider luminous quasars. So I calculate the number of lens quasar we can detect in these surveys. This number is about 20 in LSST, redshift beyond 6, and about 10 in Euclid, and about 2 in Roman. And I would say that's probably Roman doesn't have a sufficient survey area compared to the other 2. But if we look at the faint AGNs, I think this is exactly where Roman shows its power. Because, first of all, we are still going to find many of them in LSST, but as I'm showing here, most of those lens AGNs are concentrated at redshift below 7. And if we want to probe, the redshift beyond 7 population, we do need the power of Roman. And Euclid, in this case, is probably too shallow to study these objects. Well, I think these numbers are pretty exciting to me, but before I go any further, I should say we need to interpret these results with caution, because the luminosity function of these faint AGNs are still highly uncertain. So looking at these numbers, they can be easily like 10 times larger or 10 times lower. And I think that's why we need Roman, right? We want to figure out like how many objects are there in the universe. All right, I hope I have convinced you that Roman has a great potential to find these lens quasars and AGNs. And I want to spend a few more words about the unique advantage of Roman plus lensing. So let's come back to this luminosity function again. If I mark the survey depths on this figure for redshift 7-ish quasars, this is what they look like. And this is without lensing magnification. And if I add some, typical lensing magnification of 4, this is their depths look like. And let me go back and forth to just let's have another look. And my feeling about these figures is that if we want to study, the faint tail of those faint AGNs, we really need a combination of Roman plus lensing. So for other surveys or for Roman without lensing, it's pretty hard to reach this part. So that is, I think, the unique advantage of Roman plus lensing. And also, don't forget, Roman has very unique advantages. And well, I'm running out of time, but one last sentence. We're trying to get prepared for the upcoming surveys by making use of current data sets to find more lens quasars, and we're making great progress. And I'm gonna put my summary here, and I'm happy to take any questions.
Thank you. Questions for Minghao? While everyone is thinking about questions, I was wondering if you actually find less lens quasars than what you expect, even with Roman. If you can derive anything about structure formation or get any constraints for cosmology.
Well, I mean, anything we can find with Roman, either if we find more or less than we expect, will be very interesting, because that means if I go back to, this illustration, it means something's wrong with, either our knowledge about the foreground galaxies or background quasars. I mean, if we do find fewer, first of all, if we have a good knowledge about the quasar luminosity function, I assume that, and if that's the case, then that means we probably are missing some, foreground galaxy population. Either there's fewer galaxies than we previously thought, or they are less massive, or it can happen in the other way. If we find more lens quasars than we expect, that means there's a hidden population of foreground galaxies, something like that. So that, I think, will be a very useful indicator of, galaxy evolution or structure growth.
One question.
Yeah, thank you for interesting talk. So about faint AGNs.
Yes.
So I agree that Roman can detect many faint AGNs. So do you have any idea about the spectroscopic follow-up? So Roman, Grism, and Prism are enough regarding the sensitivity?
Yeah. So I think, well, I have listed some depths here, but these are all for imaging. Obviously, Grism and Prism spectroscopy will be shallower than these. So, my personal suggestion would be, like, for the brighter end of the AGNs and also luminous quasars, we can use the Grism and Prism to do the job. And for fainter ones, we can probably primarily rely on the imaging, rely on the sharp PSF to do a good candidate selection, and then we go to JWST. That would be my personal recommendation.
Any more questions here or online? I don't know. If not, let's thank the speaker again. Minghao. Thank you very much.
So, take this off. Hold.
Cool.
Okay, hi.
So next speaker we have Weizhe Liu, who is also going to tell us about high redshift quasars, and particular with Roman and Rubin. We have 10 minutes.
Okay, I hope everyone can hear me clearly, right? Okay, good. So, first of all, I'd like to thank the organizers for giving me this opportunity to talk about my works on this Roman approach for the quasar frontier, where people in front of me already introduced a lot to you about what quasars are. And here I'm mainly focusing on trying to pushing the quasar frontier, which means going to the further redshift that we can reach and to the faintest magnitude that we can reach. So I'm a grad student from University of Arizona, and here below I list the collaborators for this work. And also I'm a team of the Europe team, which we focus on the study of the earlier supermassive black hole in the universe. So first, why do we care about these high-redshift quasars? So on the bottom left, I show you some of the very popular theories trying to explain the growth of the supermassive black holes in the high redshift universe, because since the discovery of the redshift 6 and 7, quasars, they are overmassive black holes, has been raising issues on how universe can grow such a black hole in such a short time. And why are they so heavy? So several popular theories trying to address these questions by coming up with several different black hole seed scenarios, trying to explain that. And on the right, you've already seen these figures from Jinyi's talk. So this is an extrapolation of the black hole growth track from the redshift 7 supermassive black holes back to the redshift 30, where believed to be the firstborn of the black hole seeds. So it seems to have some favors on some popular theories, but it cannot completely rule out the other possibility yet. So all of the quasars that we recently discovered at redshift 6 and 7, they are all luminous, bright quasars, heavy. So they are missing a bunch of populations of they are a little bit less massive than these overmassive black holes, where we refer to as the faint quasars. So my work will then primarily focus on this. So what is the question that I want to answer? So first, I want to understand how these supermassive black holes can grow to such phase in the redshift 6 and 7 universe. So on the bottom right, I show you a number density profile of as a function of redshift of quasars. And from Jinyi's talk, we already learned that. So this high redshift quasars is becoming less and less. There seems to be collective evidence of these quasars being less and less in the higher redshift universe. And this is up to the measurement has been up to redshift 7 over here from Roman2023 observations. So the first question that immediately arises is, can we ever find any quasars at redshift above 8? And if yes, then how do we find them? So there are already Euclid predictions work on trying to search for the luminous bright quasars at redshift 8. And also there is also a recently Rebecca Lawson's paper on finding redshift 8.6 AGNs possible. And so there seems to be some possible quasar that we can find at redshift 8. So that is the bright part. Then how do we deal with the faint quasars? Are there any missing quasars that we haven't found and they are faint and they are more abundant in most of the case? So can we find them? And so there are already an ongoing ShellQ project from the Hyperspring Crime Strategy Survey programs trying to look for the low luminosity quasars. So my interest is trying to see if Roman can help to target these two questions on finding the most highest redshift quasars and also finding many faint quasars that can help us constrain their population statistics. So traditionally, the classic method that we can find quasars is finding through dropout methods. So these high redshift quasars, they are primarily not detections in the blue bands. So here I show you one of the quasar frontier at redshift 7.6. So the quasar is literally not detected in the first 3 optical images, but clearly detected in the infrared image. So the very known dropout methods. And below I will just show you the spectrum. So to actually find these high redshift quasars, we definitely need a deep enough wide field surveys that can help us probe to the dropout in the opticals and also in the infrared to actually detect them. Okay. So 2 of the surveys that we've been taking in mind is first, we need deep optical, right? So we go for the Rubin telescopes where the legacy surveys of time and space is going to map like 20,000 square degrees over the sky. So, and it can reach around 26 magnitudes. So it's really deep enough. So for the infrared telescope, we consider the Nancy Roman Space Telescope, which we provide like large enough square degree area, 2000, good enough. And it probes down to 27 magnitudes that really give you a depth to actually discover them for those faint targets that are not usually being probed by the previous wide field survey, which is 4 to 5 magnitudes shallower. But even with Roman's and Rubin sensitivities, we are still limited by contaminations, right? Because we've been optimistically talking about searching for quasars, but practically, we need to spectroscopically confirm them. And that was and contamination comes into play when you try to do spectroscopic follow-up. So here I show you a spectrum of one of the redshift 7 quasars simulations, and also some of the contaminants most seen contaminants in our quasar surveys, which is galactic dwarfs. So if we simply using dropout method to select these high redshift quasar candidates, all of these quasars and these galactic dwarfs will be picked out by similar dropout methods because of these prominent red colors of the Lyman break and all those rising up of the emission line, absorption lines. So they will be easily picked up by these dropout methods. And also you can, on the right also shows you what are the relative abundance of these populations. The blue and the greens are the low redshift galaxies interlopers, and then the greens are the galactic dwarfs. The red is the quasars. And as you can see, both galaxies and the galactic dwarfs are like several orders more abundant than the quasars. So even if you carelessly select any contaminants go into your quasar candidates, the spectroscopic follow-up can be a tragedy, right? You just cannot rule out them completely before you're doing a spectroscopic follow-up, and that will take you a lot of time to confirm them, which is very impractical. So our experience from the past is like redshift 6 plus 6.5, the spectroscopic success is like 30%. You can capture 3 quasars out of like 10 candidates. But the situation becomes much worse and worse when you go to like higher redshift and fainter magnitudes. They become a lot worse. So we definitely need to improve the understanding of these sources. And when we're trying to improve our selection methods using these Rubin's strategies and wide field surveys and photometric data that are available to us to trying to improve our spectroscopic success rate in this case. So our strategy is first, so we simulate all the quasars, galaxies, and browsers with some models, photometric flux, colors, and densities, and all of these constraints are from observations. I don't have time to talk about much detail about it. You can definitely come to me if you need more details. So, and we create more catalogs to determine our selections methods and how the completeness and efficiency behave as functions of magnitudes. So here on the right, I shows you the model surface density that we created. So there are 2 things that I would like to get your attention on is first, if you look on the red lines, they are now 2 popular quasar luminosity functions. And in one scenario, they favor a more faint quasars model, and the other one is favor a less faint quasar models. In our studies, we favors the less faint quasars model because they include more low luminosity quasars in their measurements. And also for the galaxies part, we favor a more faint galaxies simulations because they did not underestimate the galaxies' contributions in the fainter magnitude and in the shaded regions where it is primarily our interest region of finding faint quasars. So here show you a quick plot of what the result can be. So the black box marks the region that we are interested. So here I show you an example of Z dropouts selections, trying to select 6.5 to 7.5 quasars, where you can clearly see that the black box capture most of the quasar that we are looking for, and the other are simply contaminants. So we use a primary color dropouts method, which are combinations of subsequent color cuts to select quasars, and we find that we get a very good, clean result at the bright end. That is good, but then we find that the contamination itself is a strong function of magnitudes. So to further reduce the contaminants, we decided to join another selections, which is a Bayesian-based model comparison, which include the surface densities of the target population as a prior in the likelihoods, and then calculate the quasar posterior probabilities. So with good understanding of the target population models, where you know exactly where they are, where you know their model colors and flux, then this Bayesian model method has successfully detected the first redshift 7 quasars, so which seems to be very helpful. So we decided to do a joint selection of these 2 where we apply the color dropout at the bright end because it is fast and effective to select a bunch of quasar candidates. And then we join the Bayesian method at the thin end to reduce more contaminants. So for our results, so on the right, I shows you the overall efficiency and completeness as functions of magnitudes. So our overall completeness in selecting the high redshift quasar is very high, like it's almost 90% down to the faint end. And we see that the color dropout provide a very clean sample at JWST, which is the current limit of quasars. And also the selections is dropped to 20% at 24 magnitude, which is still good, 2 magnitude deeper than current surveys, and where brown dwarf is the main contaminants. And if we go further, the contamination is much higher, where the low Z interloper will now be our contaminants. And JWST can detect first redshift 9 quasars if they ever exist in the universe. So we also try to see if proper motions can help. So with the high latitude wide area survey, with like the maximum temporal separations of 4 years, the first exposure in the first year, the second exposure in the 5th year, we can maximize the proper motion analysis to detect brown dwarf. We can reject more brown dwarf at the bright magnitudes. So this study will detect 200 quasars at redshift greater than 6.5, and we're looking forward these thin quasars to provide the constraint on the thin quasars slope, where we can determine the number of thin quasars in the universe. And on the right, I show you what is the vast difference between two different population quasar agnostic function model predictions on the quasar numbers. So what will be the JWST role? So as we said, we want Roman core community survey as a survey machine. We want JWST as the good redshift spectroscopy machines. And there are already some studies on trying to get this low luminosity quasar AGN's properties. And there's several papers already discussing that and some pioneer works. And about the quasar host galaxy and feedback on these quasars, then you can see Weizhe's talk later, which will tell you more detail about that. So I've simply put my summary here and welcome any questions. Thank you for listening today.
Thank you very much. So questions in the audience or online? While everyone is thinking, did you think about synergies with radio surveys and including radio data into your selection function for quasars? If you care about radio at all.
Currently not yet, but that will be an interesting point on doing that. If there is ever a synergy between Roman and radios. Yeah, because radio can give another aspect of finding this quasars too. Yes.
If not, thanks the speaker again. Let's thank the speaker again.
Thank you.
So just put it here. Yeah, just full screen.
Slide show me what a slide.
Oh, what? It's working.
So next up we have Weizhe Liu, who's gonna tell us about the host galaxies of high redshift quasars.
Hi everyone, can everyone hear me? Okay. My name is Weizhe Liu. First of all, thanks organizers for giving this chance to talk about our recent work on quasar host galaxies. And I'm a Jasper postdoc at University of Arizona. I'm currently working on Shockwave Finance Group and the Erebus team, mainly on the studying quasar host galaxies from across cosmic time. And today, I'm going to talk about unveiling the quasar host galaxies at cosmic dawn with James Webb IFU observations. So it's not working. Okay, as already have been talked about a lot, we heard that we now know that there are very numerous quasars with 10 to 9 to 10 solar mass black holes already exist within the first billion years of the universe. But we still don't understand how these supermassive black holes and their host galaxies come into being within such short period of time. And that is my motivation of my research. And in the local universe, as shown here, there's a tight correlation between the mass of supermassive black holes and their host galaxy mass. And this kind of suggests that the black holes and their massive galaxy hosts may co-evolve with each other across cosmic time. However, we do not know how that happens. And it is vital to look at the earliest quasars at cosmic dawn when both these supermassive black holes and the massive galaxies are just starting rapidly forming. And then we can understand how they interact with each other. And at the present, we seem to know a few things. Here are two examples. On the left, this colored data points are the location of this hypertrophic quasars in this black hole mass versus galaxy mass diagram. It seems that these early quasars have undermassive host galaxy compared to their supermassive black holes when we compare to the local scaling relations. So it is likely that we are seeing an early growth of the supermassive black holes compared to their host galaxy. But however, it's also likely that we are only picking out the most massive ones that are most luminous in the universe, and there's some selection effect to it. And in addition, on the right side, we're looking at the star formation rate of these host galaxies as a function of the quasar UV luminosity. So basically what we see is that the star formation rate of this quasar host galaxy at cosmic dawn can range from several tens to several thousand solar mass per year, which means that they are forming stars very rapidly. So taking this all together, I want to argue that these quasar host galaxies at cosmic dawn may be the best place to witness the growth of first generation of massive galaxies and how they interact with their supermassive black holes. And that is where, before this James Webb era, most of the results we just seen are based on the sub-millimeter observations, which focus on the cool gas and dust within the host galaxies. We are still missing the stellar component and the neighbor line emission from this host galaxy, which can be probed by Webb. And here we are carrying on this very deep IFE observations on two of the Redshift 7.5 or so quasars from the only three known at the Redshift range from this Quasar Frontier program GL7064, which has already been mentioned in Jinyi's talk earlier. And basically, we got very deep IFU data. As I shown here, for the IFU, you get a data cube, which has 3 dimensions, 2 in the spatial dimension and 1 in the spectral dimension. And for each spatial location within the source, you can get a spectrum like that. And so our observation have a spatial resolution of R about 1000, so medium resolution. And it has probed the reservoir optical, very suitable to probe the stellar continuum and nebulous line emission in the host galaxy of these quasars. But before we can really see the host galaxy emission, there is only one challenge. That is, the quasar is so bright. Basically, a quasar is a point source. So basically, this is a Y-line image of this one of the Redshift 7.5 quasar from our program, and we stack along the wavelength range. And basically it looks like very similar to a pure PSF. So what should we do to really subtract the quasar and see the host galaxy? And this is how we do it. So basically I'm talking about a technique used in this one software called Q3D-FET. The idea is kind of straightforward. So we have this IFU data cube. So for each spectrum from this IFU data cube of each spatial pixel, the spectrum is mainly made up of like 3 components: the quasar emission from the PSF, the host galaxy continuum emission, and the emission line from the host galaxy. So what should we do? We just first of all, we can build a quasar spectral template from the innermost region of this IFU data cube, where the emission is basically pure quasar emission. And then for each spectrum extracted from the IFU data cube, we can fit it with 3 components: a quasar template with a scaling factor that's free to run, and some polynomials representing the host galaxy continuum emission, and then finally a set of Gaussian functions representing the emission lines from the host galaxies. And by doing this kind of iteratively again and again, we can finally subtract the quasar and see the host galaxy emission. And that is a preliminary result we see in one of our sources, J1007 plus 21. It is what Redshift 7.5 And here we are looking at the host galaxy Axion-3 emission line in the rest frame optical after the quasar has been subtracted. From left to right, we're looking at the emission line flux, the velocity dispersion, and the central velocity of this emission. And the peak quasar emission is indicated by this red cross there. So we're looking at this map, we kind of notice that this emission is kind of extended on QPC scale, and also it seems to be offset from the quasar center. And the line width is quite large, with median velocity dispersion of 400 kilometers per second, and is highly blue shifted, with velocity down to minus 1,000 kilometers per second. So it is likely that we are seeing all-flame gas driven by the quasar in this galaxy. So if that's true, we can compare the properties of the outflow detected to other AGN or quasar-driven outflows in low redshift universe. And here we are looking at the alpha velocity as a function of AGN luminosity in the left, and the kinetic energy alpha rate as a function of AGN luminosity on the right. So our object is a red star, and the two triangles are some recent discovery of two redshift 6.8 quasar which also have outflows. Other black data points are from low redshift AGN-driven outflows. And you can easily tell that this object fall in the range of other AGN-driven or quasar-driven outflows at low redshifts. So this kind of supports the idea that we are really, this blue shifted and broad emission we see are really come from this fast quasar-driven outflow in the source. And this also implies that such quasar feedback from quasar-driven outflow may already take place in its earliest generation of quasars. And in addition, another thing we can see from our data is that the galaxy is likely compact. So here, this red data dot means the size of the outflow of our source, and this downward triangle indicates an upper limit on the stellar quantum of our source, which we have not detected any extended quantum yet. So it's the upper limit. And in comparison, the black data points are low redshift AGN studied before, and the black dashed line is a redshift evolution of the sizes of star-forming galaxies as from this study. So we can see that the size of this our object is likely compact and similar to those star-forming galaxies or AGN in the similar redshift. So finally, just want to emphasize that in order to better understand this quasar host galaxies in this cosmic dawn or reionization era, we will need a larger sample, a more diverse sample of quasars at this high redshift. And that's where Roman can help a lot. As we have already heard about already in a previous talk, Roman will definitely help us find more quasars in the early universe that can help us further this study. And that's my talk. I will stop here and happy to take any questions you have. Thanks.
Thank you very much. Questions here? Yeah, one question.
Thanks. Oh, thank you for the exciting results. So I see that in the beginning of your talk, you mentioned the M sigma relation and the star formation rates of these, I mean, for generally high redshift quasars. And now you have oxygen-3 lines. Is there any way to, measure the velocity dispersion or star formation rate using this line and compare it to ALMA observations, if there's any?
So, very nice question. So for this one quasar, I think it's not really possible because I'm arguing that it's more likely due to the outflow. So it's not a virial motion at all. So if it's not a virial motion, I will not trust any dynamic mass measured from the emission. But hopefully, if we can have more data on this, then we can have maybe a velocity field or more regular velocity, and then we can have a better measurements and compare them to the ALMA observations also. But that's a very nice point. Thanks.
Have you compared the features of outflows using other like narrow emission lines, like the narrow H beta? Have you first detected narrow component for the H beta?
Not yet, because we are still working on data. But for now, the only most promising detection is the option 3. H beta, we don't have a clear detection yet, because you have very broad H beta there. It's kind of difficult to distinguish H beta from the host galaxy or from the quasar itself. But option 3 is the forbidden line, so it's much easier to get. It cannot come from the borderline region, so it's much easier to be seen in our data. But we are still working on that to see if there's a H beta detection, or we can put a nice upper limit on it.
Yeah, because we because we know there are some anomaly for the O3. So probably, what is the wavelength coverage for this object? Have you can you like trace the H alpha?
H alpha is in the Miri.
Okay.
So I think Jinyi's data, and I think we will be working on the data to see if we can see the spatially resolved results. Now we see the integrated spectrum.
Got it. Thank you.
Mm-hmm.
We have time for one last quick question. No, let's thank the speaker again.
Thank you.
And I believe next talk is online. Can you share your screen, maybe? Yeah. Also, yeah, we don't hear you.
Micaela, we're showing you as unmuted, so I don't know if the problem is on your end. Still can't hear you. Could try logging out and back in.
I'm back. Can you hear me?
Yes, great. And
okay, excellent. Sorry about that. That works in testing, but not live. Okay, can you see my screen okay?
Not yet, no.
Still no? I'll try again.
No, it's still not there.
Okay, it says that I'm... Let's see. One more time, sorry. about now?
Yeah, we can see your screen now.
Oh goodness. Okay, thank you. Sorry about that. All right.
Yes.
Well, thank you. Sorry again for all the technical problems here. I really want to thank the organizers for this invitation and also for their flexibility in presenting remotely and extreme patience with me as I responded to everything quite slowly, trying to learn how to refunction with a very young infant. Anyway, so, and thank you all for your patience with these technological problems too. So I'm Micaela Bagley. I'm a postdoc at UT Austin working with Steve Finkelstein. And today I will be presenting some results from the SEERS and NG-DEEP surveys with JWST, and also some results and work done as part of the Cosmic Dawn SIT that's led by James Rhodes and Sangeeta Malhotra. So just sort of taking a step back and looking at some really broad questions, I'm really interested right now in looking in addressing when the first galaxies formed in the universe, how quickly did they build up their mass, and what was the galactic contribution to the reionization of the IGM. And answering these questions or addressing these questions really requires that we understand the population of galaxies, both faint and bright, so understanding how stellar feedback affects the faint end, how AGN feedback affects the bright end of the luminosity function, how star formation efficiencies play a role. So it really requires that we start to sample the full population of galaxies. As we heard from Yuichi's excellent talk, this is strongly connected to the cosmic star formation rate density. So I'm showing here a plot very pre-JWST results, but this is a plot showing the cosmic star formation rate density as a function of redshift. And what's important to note here is that, up to redshift 8, observations generally agreed, and at towards higher redshifts, observations started to, this is all pre-JWST, but observations started to disagree. And so where some observations were favoring a more smoothly declining star formation rate density, and some were favoring a more rapid decline. And as we've seen from results today and in recent papers, this dichotomy is being pushed out to even higher redshift with JWST. But the real question here is, how can we explain the density of galaxies that we're seeing in the early universe based on their star formation efficiencies? And so looking at the density of galaxies that we're measuring, I'm showing here 2 luminosity functions. In the upper right is focusing sort of on the bright end of the luminosity function using shallow HST pure parallel observations, and then focusing more on the fainter end in the lower left luminosity functions from Finkelstein et al. 2015. What I'm showing these, there are of course many great studies to look at here, but what I'm trying to highlight is that the densities that we're measuring pre-JWST were a little bit all over the map. In some cases, this was results varying by survey strategy, but in some cases, like in the lower luminosity functions here, what we're looking at is a real variation pointing to pointing. And so we're looking at variations in the field to field variations. And so our results as we push to fainter magnitudes in the luminosity function are being affected by cosmic variance. This becomes really important if we want to understand what the galactic contribution was to reionization. The way we would do that is integrating down the UV luminosity function to some low magnitude limit to determine the density of non-ionizing UV photons. And then under some assumptions of models and models on ionizing efficiencies and escape fractions, we can start to understand what the available ionizing budget was from galaxies. But this all is determined or depends on us getting a really robust measure of the faint end slope. So I'm going to jump gears ever so slightly here to talk about the Cosmic Evolution Early Release Survey, or SEERS. SEERS was an ERS program, or is an ERS program, that was designed to get extragalactic data to the astronomical community right away. I'm listing here the PI, Steve Finkelstein, the co-Is, but it's really a team of over 150 scientists, and this image here is from our recent collaboration meeting this past month. SEERS, just to briefly describe what the survey is, SEERS has this, we're observing in the EGS field Observations came in a couple of epochs, some in December, some in June, a few more in February of 2023. We have 10 plus pointings depending upon how you count, with a variety of different prime parallel combinations of different instruments. And this figure here shows just sort of like the super chaos that became the final survey. I think this version is called like version final _2, version final, really final. But I'll break it down a little bit here just to show what we're working with. So we have 10 NIRCam imaging pointings shown in blue on the left. 4 of those also have NIRCam wide field slitless data. We have 8 MIRI imaging pointings, and we have 6 near-spec pointings, even though there are 8 in that figure. That's because, again, we had data taken in a couple of different epochs, but we're still counting them as 6 pointings. And I just want to highlight the folks who are really working in the trenches trying to get these data products reduced. I'm working on NIRCam imaging. On the slitless spectroscopy, we have Nor Perskal. Guang Yang works on our MIRI data, and Pablo Arabajaro works on our near-spec. Quick plug for Sears. If you're interested in anything, our science, our papers, our data releases, check out our website. You can find us on Twitter if you're still there. You can access our data on our website. We're also on MAST. And we have a paper out describing our NIRCam data reduction, and all of our reduction scripts are on GitHub. So check that out. But why Sears? Why talk about Sears? So just like there's a lot of disagreement in the observations, there were a lot of there was a variety of predictions pre-JWST of what we would see from models. And Sears is sort of optimally designed to constrain the models predicting galaxies, the galaxy density in the early universe. So given if the real question when we first got our data was, will we detect high redshift galaxies? And high redshift here, I'm saying greater than 10 or so. So this image that I'm showing is our mosaic from the first 4 pointings we got in June. And really right away, like almost day one, we found a high redshift galaxy. This is a galaxy candidate at about redshift 11. It is named Maisie's Galaxy after our PI's daughter, because we sort of just selected it on her birthday. And it is a surprisingly bright galaxy candidate that was really not predicted by simulations. So what I'm showing on the right here is a figure showing the predicted number of galaxies greater than redshift 12 and brighter than the brightness of Maisie's Galaxy from a variety of simulations. These include hydro, semi-analytic models, and semi-empirical. And really, none of them would have predicted that we found this galaxy. You know, the Beruzzian Silk model gets if you remove all dust attenuation, which is what that fainter bar shows, then you would start to see this. But really, this was sort of unexpected and starting to indicate really early results that we're seeing a lot of extra star formation at redshift 10. So using those first 4 pointings, we got our first set of high redshift galaxy candidates. I'm showing their magnitude and photometric redshift distributions here, and Maisie's Galaxy is the one with a star. And we were able to get our first luminosity function. So the Sears measurements here are shown in red. Other JWST surveys were shown in orange, and HST and ground-based surveys are shown in light blue. And the blue curves are showing an evolving double power law luminosity function that's fit to data from redshifts 4 to 8. And the shaded region extends that extrapolation down to redshifts 9 to 12. And what we see here is that the Sears data points, even though in the inset graph we can see that the P of Z's are peaking around redshift 11, the Sears data points really exist at the upper envelope of what's expected for redshifts 9 to 12. So this could be evidence that we're seeing this evolution in the luminosity function just really slowing down as we get to these redshifts. Then we got, in December, we got the rest of our 6 pointings, and so here is showing a full Sears 7-color mosaic of all 10 pointings. And naturally, what do we want to do with that but look for more high redshift galaxies? So what we're showing here is our sort of complete redshift greater than 9 galaxy sample, or sample of galaxy candidates. There's 89 of them. And I will come back to talk about this in a minute, but the squares in this figure show those that have been spectroscopically confirmed. However, Sears by itself has a fairly narrow dynamic range and magnitude, and so we want to combine it with the NG-DEEP, or the Next Generation Extragalactic Exploratory Public Survey. So this is a program that is PI'd by Steve Finkelstein, Casey Papovich, and Nor Perskal. It comes in two parts. One is an ultra-deep nearest slitless spectroscopic survey on the HUDF, and that is Nor Perskal is working with the reduction and calibration of that data set. And then the other part is an ultra-deep near-cam imaging survey on the UDF parallel field. So this is the deepest I-band imaging in the sky, and the near-cam parallel just perfectly aligns with that. And this data set is being worked, Leong is leading that effort. So the main science goals of NG-DEEP are to constrain the feedback mechanisms in low-mass galaxies across cosmic time. And on the nearest side, we're looking at measuring the slope and the scatter of the low-mass end of the mass-metallicity relation at low redshift. And on the near-cam side, we're looking at measuring the slope of the faint end of the UV luminosity function. So NG-DEEP also has been observed in 2 epochs, and we only have half of the data so far, but we're already able to add about 1.5 magnitudes dynamic range to the UV luminosity function. So this is a figure from Leong's paper. It came out early last week, showing the luminosity function, including NG-DEEP in red circles there. And when we combine it fully with Sears, we see that NG-DEEP really does agree with the sort of slowing evolution of the UV luminosity function. Another way to look at this is in the surface density of galaxies. And so this is showing the cumulative surface density as a function of redshift using the Sears data. And again, we've seen this in Yuichi's talk, we've seen this in a lot of talks today and other JWST papers. The JWST results at high redshift are higher than can be predicted by existing models of galaxy evolution. So how can we explain this? Well, one clear thought would be low redshift interlopers. Are our samples very highly contaminated? So we'll just jump right to that and say we don't think so, but certainly we need a lot more spectroscopy to follow up to confirm. These are figures from several Sears near-spec follow-up of candidates in the EGS field, spectroscopically confirming them between redshifts of 8 and 9 or so, 8, 9, and 10. Including Maisie's galaxy in the upper right. And so we can sort of tentatively conclude that it's not entirely low redshift interlopers that's causing this. We heard from Jinyi, a great example of how we're seeing a lot of low luminosity AGN in galaxy samples at high redshift. And this is showing an example from a couple of papers. Rebecca Larson's and Dale Kuchevsky's seeing some broad components, spectroscopic components in our near-spec follow-up. These are sources that have photometric SEDs that are dominated by stars, but they have spectroscopic signatures of AGN. So and we're seeing, and as we've heard today, we're seeing plenty of these low luminosity AGN, very, very red sources, SEDs that need to be fit by multiple components. And so there's a lot of exciting work to be done here to really start to quantify the AGN population. We've also heard that more efficient star formation could have a huge role to play here. And so I'm leaving these as just open questions that we want to explore. Cycle 2, cycle 3 with JWST, and then of course with Roman. So how will Roman help? And so from now on, I'm gonna to sort of finish by talking about work that we did as part of the Cosmic Dawn SIT. Again, this is led by James Rode and Sangeeta Malhotra. And the question was, where is Roman's place given all of the results that JWST is providing? So I'm bringing back the Sears plus NG-DEEP luminosity function to show the purple box now is highlighting the sort of phase space that the high latitude wide area survey will be able to probe, sort of assuming a magnitude limit of 26.9 and a redshift of 10.5. So we're seeing that it's going to be incredible at really nailing down the bright end of the luminosity function. And that's so important. These bright galaxies are very rare. They require large areas to really sort of sample the full population. But you'll notice that the rest of the luminosity function is really, untouched. And so what we need is a deeper surveys to help constrain both the Ni and the faint end of the luminosity function, especially as we push to higher redshifts and we want to use these luminosity functions to understand the ionizing photon budget during the epoch of reionization. So this motivated, a project to really look at, what could we get from a Roman deep field? And we went about this using the Santa Cruz semi-analytic model for galaxy formation. And I'm going to sort of skim through some of these summaries about what the SAM gives us, and really point you to Aaron Young's recent paper from 2023 on describing this 2 square degree light cone and providing multiple iterations of it, and also see his talk on Thursday for sort of the next generation, better and better SAMs that he keeps creating. But the SAM that we're using for this survey is based on the multi-dark suite dark matter halos, and from that is constructed a 2 square degree light cone that goes out to redshift 10. And the Santa Cruz SAM is used to use predicted physical properties. They're forward modeled through the Roman SED filters, and provides a catalog of Mach photometry that also has source positions that are fully motivated by the dark matter halos underneath. So just to sort of visualize what we're talking about here, we all know that the Roman field of view is quite large and is going to help a lot in these types of surveys, but I think it really helps to visualize it. So what I'm showing here is a snapshot of the SAM in between redshifts 6.5 to 7.5, and all of the galaxies down to a limiting magnitude of the HUDF, so 29.5, are shown in black. And then the positions of sources that would be observed if you looked at this field with, say, HST, are shown in orange. We've got two sort of WIFCAM3, WIFC3 pointings here in orange, and then one very simplified Roman field of view, but it has the same aspect ratio, one Roman field of view. And so what do we get when we measure what we see here? So zooming in, we can see that one of these HST pointings is in sort of a region that's underdense, and one is in a region that's overdense. And we see those results come out when we look at the UV luminosity function on the right. So the black line gives us sort of the true value of the light cone, the full light cone, all 2 square degrees. And the purple dashed line in the squares are showing us what we would measure with Roman looking at this pointing. And the orange we can see from HST, one of the pointings would give us a density that's quite high and one that would give us a density that's quite low. And so the power of Roman here really is sort of marginalizing over all of the density variations in this pointing. So we're looking at, what would it take to do a Roman deep field survey? Let's assume that we have 500 hours to play with. And what is the optimal compromise for high redshift galaxy searches between survey area, depth, and filter coverage? So we've considered 16 surveys. We're covering 4 different areas, which is approximately 1 Roman pointing, 2 pointings, 4 pointings, and the full light cone, which is sort of 7 pointings. In each of those areas, we're looking at 4 filter sets, a base set that uses Z, Y, J, and H, a set that uses the R-band filter, a set that adds the F184, and a set that adds both. And here we can see, so we're seeing the area and magnitude we're seeing a plot showing the area and magnitude that would be probed by these 16 surveys in the context of other JWST surveys in black and HST surveys in orange. And you can see that this Roman deep field would occupy a really unique phase space here of going deep, but also going wide enough to start to probe some of these important results. So I'm going to really briefly summarize some of our results here because we have a paper that will be coming out soon, and I'll defer most of our discussion to that. But what we've done is for each of these 16 surveys, we photometrically scatter that whole 2 square degree light cone. Then we mock observe the galaxies. So we photometrically scatter them, then we run them through a full high redshift galaxy selection process using the full, using photometric redshifts and detection significances in different bands. We do a full completeness analysis, a full contamination analysis, and here we're going to show just a couple of the results. We do this for all 16 surveys, and the goal is to find, a sort of a sweet spot in these survey designs. So focusing first on the recovery, we know exactly what truth is. So looking at the different filter options, this figure is showing for one Roman pointing, what you would get for recovery as a function of F185 magnitude and redshift. And we're seeing the 4 filter sets. And you may notice a few things. The recovery at the low redshift end around redshift 6 is really quite poor at all magnitudes in the left column. And that's the column that does not use the R filter. So it's not particularly surprising, but this really does demonstrate that the R filter is needed to detect dropout galaxies at redshift 6. We can also see that the recovery is a bit low in the top row at the high redshift end and sort of towards fainter magnitudes. And that's the row that is not using the F184 filter. And so once you get out to redshift 9 or 9.5, you really do need that 184 as a sort of an additional second detection filter. We can compare that with the contamination of galaxies in these samples, because having high completeness is great, but not if you're swamped by contamination. And again, we can see that in the right column, we really are swamped by contamination at redshift 6 when we don't have that dropout filter. So this is sort of, again, I'll defer to the paper for our full results, but this is sort of demonstrating the play between the different pros and cons of each survey. So now I want to show a few of our results from the luminosity function. So this is showing luminosity functions measured in, again, a single Roman pointing using all 6 filters. And at redshifts 5, or about 6, 7, 8, and 9, sort of decreasing in density and color. The solid, the thicker black line, or the thicker colored line in each redshift bin shows the fit to the unscattered full light cone. So this would be the true luminosity function with 100% completeness and 0% contamination. And then, the thinner lines are showing the measured luminosity function that we get in 4 realizations that each cover 0.28 square degrees. So we're seeing that they do generally recover the true value, but there is still some scatter in there. And so sort of finding a way not just to minimize contamination and maximize recovery, but really find the filter set in the area that allow us to fully constrain the luminosity function. And again, we're looking, this box that I've put on here shows where the high latitude wide area survey, sort of 5 sigma limit, now plotted for about a redshift of 9, would land. And so we do see that that would just constrain the bright end. It would really help nail down that bright end, so it's going to be important to combine results. But it does not leave, it still leaves us in need of a deeper option. So we can take those luminosity functions, integrate them down to some limit. I've chosen -17 here, and see what we get for the integrated non-ionizing UV luminosity density. And so that's what's shown here. So the solid black line is again the value measured from the full unscattered light cone, and the purple hashed region shows what we're measuring from photometrically scattered and observed and selected through our high redshift selection process galaxies in a single Roman pointing. The plot is showing rho UV as a function of redshift, where rho UV is on a logarithmic scale. And so we've sort of put slices at each redshift bin to show you what that looks like on a linear scale. And you can see that those Roman values, there is some scatter, but they are, they hug the true value, they bracket the true value quite well. So, one of the sort of questions here is that JWST is really good at going deep quickly and efficiently. So why do we need a Roman pointing to do that? Or why do we need a Roman deep field to constrain the faint end of the luminosity function when we have NG deep and we have JADES? Well, what we can see if we look at what we would get sort of with synthetic JWST observations is that even Sears and NG deep together are still just one realization, one observation of a single, well, Sears plus, because we're sort of stitching together the two magnitude ranges to get the full dynamic range, but it's still just sort of one pointing. And JADES would have a second pointing, but JADES and NG deep, at least in one region, are quite close. So, how swamped by cosmic variance would our results be if we relied just on the JWST deep fields? And what we're seeing here is that we would be fairly swamped. We're seeing the same thing we saw before for Roman and the full light cone, but the orange is now showing what you would get for sort of a Hubble frontier field plus HUDF survey. So this is now combining 8 different HST-sized surveys together, and then doing multiple realizations of that. And the gray region shows you what you would get with multiple realizations of a Sears plus an NG deep. And it's really important, I think, to point out that these Roman results are scattered. They've been photometrically scattered and reobserved. These Hubble and JWST results are not. They're completely unscattered. So this is like the best case scenario for the JWST results and potentially the worst case scenario for Roman. And it's really exciting to see how much better Roman does with this type of a deep field. So with that, a little bit of a whirlwind here, but I'll summarize briefly here where, we and everyone is finding a very high abundance of bright galaxies with JWST. This seems to be implying that the UV luminosity function the evolution of it is slowing as we get to higher redshift. There's a lot of really exciting reasons that this could happen. We could be seeing increased star formation efficiencies. We could be seeing contributions from faint AGN. We could be seeing a changing of the IMF. There's a ton of possibilities to explore and a lot of really great questions to answer in the coming years. And JWST is great for this, but it's really ideal for deep studies in small regions. It's ideal for spectroscopic follow-up, for deep imaging follow-up, but you really need, a much wider area, but still deep coverage to really get down to the faint end of the luminosity function and overcome cosmic variance. And so using the Santa Cruz SAM, we've sort of done some mock observations to show how much improvement a Roman deep field would give us in this type of study. So I will end there and take any questions. Thanks again for your patience.
Thank you very much. There is time for a lot of questions. Yes, there is one question. Right.
Thank you for a wonderful talk. I'm very impressed that you can give this talk with a baby. But that's not my question about how you did that. I'm very interested in the potential contribution from faint AGN. And I was wondering if you could say a little bit more about the SED fitting to estimate the AGN contribution to the bolometric luminosity. In particular, if you did any calibration with like X-ray stacking or something like this. Thank you.
Yeah, that's a really great question and a little bit outside of my expertise. I would love to defer that question to all of the wonderful talks we had this morning and the real experts on AGN. But I can say that we have seen through the Sears data, we're also seeing these sources in NG deep, and I know they're being found everywhere. That we've had to really change how we fit SEDs and adding in multiple components, some dusty star-forming galaxies, some heavily obscured AGN, and really sort of combining a very, very blue component with a very, very red component to fit these data in ways that we haven't before. I think there are there are X-ray observations for a subset of this sample, but I don't know the specifics. I don't know if that answers your question.
Yeah, thanks. There's one question online.
So this is a question from Ethan Siegel. The early JWST results you are looking, you're talking about represent only a tiny fraction of the deep JWST data that will be available by the time Roman launches. When one accounts for the future incoming JWST data, will Roman really teach us anything we won't already know about the faint end of the high Z luminosity function, say 5 to 10 years from now?
Yeah, that's a really, really great question. I think my answer is just I'm so excited to see what both JWST and Roman get. I think that we will see far more JWST deep surveys coming through in the next 5 years, of course, but each one will still be limited to a relatively small area. To go deep in that kind of time, you're looking at still single pointings. And while they're very, very helpful and useful in getting that faint population, single pointings are still going to be very affected by cosmic variance. And so I think we will still need a Roman-sized deep field to, maybe in 5 years we find that we don't have to go quite as faint if we can combine it with all the JWST deep fields, but we will still need some component that goes a lot deeper than the high latitude deep survey to really minimize the effects of cosmic variance on the faint end. That's my opinion.
Thanks. Any more question here, the audience? If not, let's thank Micaela again for the presentation.
Thank you, everybody.
So this ends the session 4B, and right now, yeah, just coffee break and then the science writer workshop, and later on there is the conference reception at 5 p.m. So let's thank all the speakers of the session again, and yeah.